Let's start with the first code. First of all, we need to write the word 0 and 0 Fourier series x dot pi. Okay. Okay. In the first place, we need to write the Fourier series example. First of all, we need to import the numpy as MP and import matplot lib.pyplot as plt. Okay. So, firstly, we need to define the functions. Function definition. Just like this one. And so, in order to represent our example, def square wave is a function with a t as a time, and so frequency components in here and amplitude must be given in here. For example, 1.0. This is a default argument, and so this must be returned to the what? The amplitude times 1 plus MP sine MP sin 2 times MP pi times frequency times t. Okay, and it must be divided by 2. Okay, this generates to the what? The square wave for a given signal. Okay, and so all the sinus can be treated with the what? The signum operator in here, plus or 0 or minus 1, and so 1 plus 1 2, and 1 plus minus 1 is 0. Okay, this creates a square wave. Okay. And so, as created in the lesson, the Fourier coefficients should be defined with the t, signal, and num terms. This is the resolution rate, or the maximum number of iteration to generate this square wave functions. Okay, and so the coefficients is created with what? The empty list in here, and for n in range of num terms an is the coefficients of the Fourier series 2 times MP traps, and the signal times MP cosinus 2 times MP pi times n times t. Okay. And also we need to give the t. This is the what? The integral form of the an coefficients, and also bn can be defined with the what? With the sinus operator in here, just like this one. And also coefficients must be stored in the append of the what? The as a tuple an and bn. Okay. And finally, we need to return the coefficients. Okay. So we need to define another function, reconstruct the signals. Okay, and t and coefficients. The signal is defined with what? MP zeros like t. What's the meaning of the zeros like? What's the difference between the zeros and the zeros like? Zeros like, which means that if we have any specific dimension of the shape of the t, which is given in here, and so this dimension is transmitted into the what? Into the zeros like, and so this signal is equal dimension with the what? With the t. This is an easy way to the what? To define the empty signal in here. And also individual terms can be created with the what? Empty list, and for n and tuple value an and bn in enumerate coefficients. So the term is equals to what? The an times mp cosinus 2 times mp pi times n times t plus bn times mp sinus 2 times mp pi times n times t. Okay? And also individual terms must be appended in this list, the term and signal must be collected with these terms. Okay? And also return signal and individual terms. These are the function definition. Okay? The main code can be given just like this one. The main code. The parameters can be given by the frequency, which is equals to 1.0, and duration is equals to 1.0, and num terms is 100. Okay? And also t can be generated with what? The mp linspace 0 to duration 100 points, which is given here, and endpoint must be assigned to the false. Okay? So in the second place, generate the square wave and fs coefficients in here. So the square wave signal can be defined with the what? The square wave function of the t and frequency patterns. Okay? Also the coefficients can be assigned with the what? The Fourier coefficients, t, square wave signals, and num terms. Okay? And reconstructed signal and individual terms can be assigned with the reconstructed signal, t, and coefficients. Okay? So in order to demonstrate the signal, the visualization first can be given in here, just like this one. The PLT figure is assigned to fixed size 12.8, and also PLT subplot 311, and PLT plot t, square wave signal, and label must be assigned to the what? The real signal. Okay? PLT title original signal. PLT X label, this is the time, and PLT Y label, this is the amplitude. Okay? And PLT legend must be opened. So in the second place, individual sinusoidal signals can be created with what? The PLT subplot 312, and for n the term should be assigned in here in the enumeration of the what? The individual terms, and so the PLT plot must be assigned t and terms, and label should be assigned with the what? The functional string term n plus 1. Okay? And PLT title should be copied in here, individual components, time, and amplitude. Okay? And also we need to create the what? Reconstructed signal. This is the tree, and this is the reconstructed signals, okay? And so this label is the F, and we need to assign the terms, num terms in here, and also the color must be assigned as the orange, okay? And so this is the Fourier series representation of square wave, okay? And also PLT tight layout and PLT show must be given in here. Okay, in the first place we need to define to the what the 5 num terms in here. And so if I run this code and then see, this is the original signal, okay? And so each sinusoidal and the cosinus term is given in the what? In the second graph. But each of them are to what are summed into the what? Into the third square wave plot, okay? But the resolution is so small in here, so low, because the 5 term is given in here. For example, if I choose to what? The 20 in here. So, in this case, and I'm sorry, this must be removed in here, okay? Because the graph is so meaningless. Okay. And so, if I choose the what? The terms 20 values in here, and so this is closing to the what? Closing to the 1 to the 0. But at the what? At the low resolution rate. But, however, if I increase to what? The num terms to the 100s. See, in this case, the 0.4 is reached in here, just like this one, okay? And so, what about this one? If I choose the 1000s values here, and so to up to what is the 0 is closing in here, just like this one, okay? If I choose the 10,000 in here, for example, in this case, we have to what is closing to the amplitude of these signals, okay? But the exact representation must be given here in the correct order of these terms, okay? And so we need to set the total values of these terms into the what? Into this one, okay? Because the trapezoidal signals is not used in here. Trapezoid. If I choose this one, and so this is closing to the what? To the result, but not the exact one, okay? Because this resolution cannot be created to the what? To the exact representation of these signals in here, because the square wave signals is equals to what? The sinus term 2 to 1. But in this case, we cannot create these square wave signals in an exact representation of these terms, okay? Any question? This is the first example of these terms, these diagrams. And so we need to continue with the what? With the another examples in here, okay? Okay. I'm trying to do some codes right now, but I will share my screen. Okay. So, in the second place, Fourier tf.py example is built, okay? For the what? For the frequency domain analysis. Okay. First of all, we need to import to the what to the numpy smp and import matplotlib.pyplot as plt. First of all, the dev create signal in here with the time points just like this one, okay? And the signal is assigned to mp sinus 300 times 2 times mp dot pi dot time points, okay? And also plus mp cosinus 100 times 2 times mp pi times time points, okay? So we have two frequency components in here, just like this one, which is, one of them is the 300 Hertz and the other one is the 100 Hertz, okay? And so return signal should be given in here, okay? And also we need to create another plot in here, plot time series, the signal, time points, and title. MPLT plot, time points, and signal should be given here. MPLT title, title, and also PLT X label should be given, the time, and PLT Y label, amplitude, and PLT grid must be given to the true, okay? So, how we can apply the discrete Fourier transform? The signal and the sampling frequency must be given in here, okay? And n must be assigned with the len of signal, okay? This is the creation of the what? Discrete Fourier matrix, which is the dimension of the what? The n, okay? And so the k is the what? mp arrange to the what? To the n, okay? This is the list. 0, 1, 2, 3, 4, blah, 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 okay? And also n, k reshape of the what? The tuple elements and 1, okay? And so w is defined with the what? The mp exponential term of the what? The minus 2j times mp pi times k times n divided by bigger n, okay? And so the print this is the discrete Fourier matrix W, okay? And also the frequency can be assigned with what? The k times sampling frequency divided by n, because this W finds what? The normalized frequency range for a given the sampling frequency rate. Just remember the what? The Nyquist criteria, guys, okay? And also we need to return to the what? The frequencies and the mp dot w and signal. This is the what? The output of the signal treated with the what? With the w signals, okay? So def plot discrete Fourier transform in here. So the signal, sampling, frequency must be given in here, and so the title should be given in here. First of all, we need to call the frequency and the Fourier transform in here, just like this one, the discrete Fourier transform, the signal and the sampling frequency must be given in here, and also the plot, the positive part of frequency, because the minus infinity to infinity is treated in the what in the discrete Fourier transform. We need to split to the what the negative part, or remove the negative part in here, and so the positive frac indices is equals to the what frequency is greater than equal to the 0, and frequencies greater than equal to the 500 or the sampling frequency rate, okay, which means that we can assign to the what divide by 2. This is the Nyquist criteria. And also the PLT plot should be assigned the frequency. Positive frac index should be given in here, just like this one, and so MP, absolute values of these terms, the Fourier transform and positive frequency. This is the magnitude of the what? The total signal, MP dot W signal transformation, okay? And so the PLT title is the title, and PLT X label should be assigned with the what? The frequency, which is in the hertz, and PLT Y label, amplitude, and PLT grid. This must be assigned with the true, okay? These are the functions. And so the main code can be given in here, just like this one. Firstly, the sampling frequency must be selected with the 1000th value, and time points should be created with what the MP arrange 0 to 1, and 1 divided by sampling frequency, okay? That's the period. So the signal can be created with what? Create signal, time points, okay? And PLT figure, fixed size 12.8, and PLT subplot 211, and PLT time series signal, and time points and time series data, okay? And after that, the PLT subplot 212 and plot discrete Fourier transform, signal, sampling frequency, and DFT up to 500 Hertz, okay? And also PLT tight layout and PLT show, okay? So if I run this code, and then we will have to the what, we have the time series signal and the what, the body plot or the frequency domain signal in here. In this case, just remember that we selected the what, 100 Hertz in here, just like this one, and also 300 Hertz in the what, in this signal. Normally in the time domain this signal is looking just like this one, but in the frequency domain, or the after the applied the discrete Fourier transform, and then we will have to the what, to the exact representation of this signal in the what, in the frequency domain, okay? For example, if I choose the what, the another sinus signal in here, for example, this is the what, the 50, for example. And then the body plot or the frequency DFT transformation shows or demonstrates us to the what, the 50, 100 and 300 signals in here. And so if I rerun this code, and then just see that we have another signal in here, at the what? At the 50 Hertz. Okay? This is how we can treat the R signal in the what? In the programming language. To see that you can easily implement this discrete Fourier transform in the what? In the microprocessor based on this information. But in the microprocessor you need to build the whole algorithm using the while and for. Not this one or not this one. Okay? Any question? If you don't have any question, and so we will continue with the real example. Where one signal conditioning example.py. First of all, we need to copy all of these terms in here. This is the what? The 100 ATR.he and XWS. This is the ECG signal data, guys. Okay? And so this is the real ECG signal, electrocardiogram signal, which is coming from the what? The real person. The ECG is the electrical activation rate of the cardiac tissue or the heart. Okay? Maybe you are, if you have tried the hospital, and so these signals is what collected from the patients, and then we can track these signals in order to what? In order to detect any abnormality of your heart conditions. Okay, but how we can analyze this signal? First of all, you need to install the VWFDB package to collect this dataset or obtain the data 100 dots in here. This is a special tool to the what? To track any biomedical signal in the literature. Okay? And so we need to also import the NumPy SMP and import matplotlib.pyplot as PLT. Okay? And so first of all, the load record using the RD record function. This is the prepared function to what? To obtain the data from the 100 dot file in here. And so the record WFDB RD record function is called with the 100 dot file and samp to the what? 15,000. Okay, this is the endpoint of the what? The R signal. After this process, we will have to what? The 15,000 points of the ECG signal. Okay, and also we can collect the annotation which is detected by the what? The doctors or the expert in the hospital. Okay, WFDB RDN. Okay. And so 100 and the ATR is the annotation file, and SAMP2 must be assigned to 50,000. Okay? And after that, the extract the ECG data using the what? The data is the record dot signal p signal. Okay? And so we have the channel 1 data 0 and channel 2 is assigned to the what? Data 1. Okay? And also we need to create a time range with what? The length of the channel 1, and the type should be assigned as the float and record.fs. Because if we record the whole data, for example 100 or the 1000 hertz in here, and so these times must be going to the what? Up to this record sample. Okay? So PLT figure fixed size 12.6. Okay, and PLT subplot should be given to 1 and 1, and PLT times plot times channel 1, and this is color B, okay? And PLT X label, time, which is given in the SAC, and also Y label. This is the voltage value, okay? Volt, and PLT title ECG channel 1, okay? And also we need to draw another channel, which is given in the watt in the another patients in here, okay? But the times should be created in here with the watt for a given channel 2 in the record signals, okay? And so PLT tight layout and PLT show must be given in here. See, this is the real electrocardiogram signal, which is obtained in the dataset of the watt of the R prescription. This is the channel 1, this is the channel 2, okay? These are different in terms of the watt, the position of the electrodes on your body, okay? But if we obtain this dataset, and so we can apply some neural network algorithms or the artificial intelligence methods to extract the information or the real or the important information from this data. For example, if the cardiologist just look at to the watt to bigger R points in here, bigger signals in here, just like this one. And so, if this is too low, and so this is a sign of any cardiac abnormalities in your body. But in order to optimize the whole algorithm based on these terms, and so we need also firstly to the watt to utilize these datasets or the libraries which is given in here, okay? So this is the watt, this is the basic example of the watt, the real electrocardiogram or the biomedical signal demonstration on the Python programming language. Please, you should install to the watt WFDB module in your Python. Just using the watt the pip install WFDB, okay? Any question? So, if there is no question, and then we will continue with the Virtue ECG Fourier series example. Okay. First of all, we need to obtain this data set just like this one, the copy of these terms, and so 360 taken in here. In this case, we will try to recreate the R ECG signal with the utilization of the Fourier series, guys. Okay, but this is the ECG 1, this is the ECG 2, okay, and this is the ECG 1. And so the R functions which is given in here, just like this one, the Fourier series, reconstruct signal, Fourier coefficients in here, just like this one, okay? This one. And so we can copy all of these algorithms in here, functions. Okay? And after that, we need to write the main code, the num terms, which is equals to the 100, and the coefficients can be obtained with the Fourier coefficients in here, the times ECG1 and num terms, okay? And also reconstructed signal, the individual terms can be obtained with the reconstruct signal times and coefficients. Okay? So, if you have the any ECG data, which is given in here, this is the real data, and so we can recreate by using to do what the Fourier series functions, just like this one. Okay? So, in this case, but remember that the important advantage of this signal, the reconstructed signal from or is important since we have many features right now. Okay? So, how we can build that visualization can be demonstrated in here. The PLT figure, fixed size 12.8, okay, and PLT subplot 3, 1 and 1 and PLT, I'm sorry, this can be copy all of these terms in here just like this one. Or we can write it again, the PLT plot, the times ECG1 and the label ECG1. Okay? PLT title ECG1, PLT X label time, and Y label is amplitude. Okay? And also we need to draw the legend PLT grid on, just like this one. Okay? And all the terms, individual terms, can be copied with this one. Okay? The individual terms T, but in this case the times must be given in here just like this one. Okay? And so this must be assigned with the terms and we don't need any label in here. Okay? So the PL, this must be copied right now. It's unnecessary parts for our study. And PLT subplot 313, okay? And PLT plot is assigned with what the times, reconstructed signal, and label Fourier series terms with the what, with the num terms. Okay? And color must be assigned to the orange with the same as this one. This is the reconstructed signal, time, amplitude, and grid must be on this case and also this case, and PLT tight layout and PLT show must be written in here. Okay? And so if I run this code see, the first graph is a real ECG signal, okay? In the second graph, we have the terms in here, just like this one. And the last graph is equals to the what? Is equals to the reconstructed ECG signal, based on the what? These individual components. But it's important to note that this real ECG signal is equals to the one property. But if we have this signal and if we reconstruct whole the signal based on this sinusoidal or cosinus signals, and then we can create or increase the number of features to be fed into our neural network, which is increased the stabilization and the classification performance of any abnormalities on this signal. Okay? This is the 100, for example. If I set the 200s in here, and so this is more equal to the real one, guys. Okay? Any question? If you don't have any question, and then we will take a break, and after that we will start at the 8 p.m. Okay?